Then we can start.
We can start? Okay, here we go. Welcome everyone and thank you for joining us today. My name is Alina. I am the head of the study office of Master of Computer Vision program at HSU University. Our program trains computer vision engineers who are able to solve all kinds of challenges in this field. And we always try to keep up with the most recent trends and to keep in touch with the real professionals. And today we have one of them as a guest, as a special guest. Dmitrii, you're welcome.
Selena, thanks for welcoming me, and hello to everyone who watches this webinar. I hope you find this info interesting and useful for your future career. So let me start with naming the topic of this talk. It is MuZero, solving Atari games with computer vision and reinforcement learning. And let me first introduce myself. My name is Dmitrii Khizbullin, and at the moment I'm an applied AI ML engineer lead at KAUST. KAUST is a university in Saudi Arabia. Its full name is King Abdullah University of Science and Technology. It's a very advanced university which partners with industry, solves various important topics like climate change, sustainable development, with machine learning techniques as well. So applying artificial intelligence to efficiently transform the society. And overall, my background is in computer vision and neural networks. Historically, I've been working at Huawei Technologies in Moscow, working on various AI-powered projects on tensor compilers, on autonomous driving. So all the breakthrough projects that Huawei has in the research center. And also my experience spans several countries like Estonia, where I was working on the vision of these cute mobile robots by Starship Technologies, and autonomous intelligent driving company in Germany, where we've been developing level 4 self-driving car in there. Right, so let's go ahead and proceed to the topic of this talk. I will be talking about a paper by Google's department DeepMind, and DeepMind is a breakthrough research department who sit in London. They are very smart and they publish fantastic papers in Nature. They have their blog. I highly recommend looking into their blog about their AI paper, about their AI projects. And if you prefer looking deeper into the technical and scientific details, please take a look at their papers. They're very well written, and DeepMind, they are very fond of AGI. So what is AGI? It's artificial general intelligence. So basically, an attempt to create the intelligent machine or an algorithm which can compete with people, with humans on the same level, in all possible fields where people operate, and eventually become superhuman in all the fields. So this is their pipe dream, and so far they are making like tiny and bigger steps towards this goal. So what methods they use to actually to solve the problem of artificial general intelligence? So normally when we think about AI, we probably think about neural networks, and they are trained in a supervised manner on the data sets and labels, but that's not how people, for example, function in reality. So people actually learn on the go. So they are not presented with the ground truth data set of what is right and what is wrong. So people just find themselves in an environment which is the world, Earth, society, and try to find their way in this environment quite successfully. So how does the typical cycle of functioning of an intelligent agent in the environment looks like? So can you actually see my cursor?
Yes, it is red.
Okay, yeah, fantastic. So an intelligent agent, it exists in the environment and observes its state. So the state goes into the agent at this specific moment in time, and based on what the agent sees, it performs some action. So this action affects environment. So environment changes its state given the action that an agent performed. And the environment changes state and produces and comes to another state, specified in the new timestamp. So this process is a discrete time process. Also not like exactly tracking the reality, but nevertheless, it's a good approximation to begin with. And the new state gets observed by the agent again, and the cycle repeats. And it repeats until infinity. And apart from the state, which an agent observes, environment gives some feedback to the agent. And basically, agent takes its feedback from the environment. It's called reward, and reward can be positive. Like, for example, if an agent is an animal finds food, there is some positive reward for finding food. If an animal faces some predator, gets scratched by the predator, for example, then they will get a negative reward. And that's how the agent actually learns to get by in the environment. So this process is called reinforcement learning, and this process in general has nothing to do with any neural networks. So it's a more fundamental process of learning, and let's see in more details what DeepMind were doing to apply this reinforcement learning framework to some real life problems. So it's very tempting to jump into something like training a walking robot to walk, or a robotic arm to grab things. But of course, you need some progression of research to actually get to that stage. And around 2016, DeepMind actually started with solving something simpler, with solving Go. Because chess is a board game which was somewhat solved in 1990s with the and with some like knowledge base and planning methods. But some board games they were not solved until DeepMind actually nailed it. And by solving, I mean getting superhuman. So basically, beating the best human players in this game. The Go is a Chinese game of capturing territory. And the progression of papers looked like this. So DeepMind started with their AlphaGo paper in 2016. It was published in Nature. Then moved further to AlphaGo Zero, and from the next year, from AlphaGo Zero, they moved to AlphaZero in a couple of years. And in 2020, they temporarily arrived to MuZero. So let's take a look what's this progression and what was going on over those 4 years. So first, since chess were sold, DeepMind selected Go as the next best candidate for solving, and there was no algorithm that was beating the best players in the world in Go at that date. So they focused on it. Then you can see that the coverage of games was increasing. So DeepMind were adding more and more games to the set that was sold by the same agent. So in the first iteration, they added chess and shogi. Shogi is Japanese chess, and then at 2020 they added Atari games. I will talk about them later, of course. So you can see that the coverage of the environments that an agent can solve is increasing. And the eventual goal is to cover all possible environments. So basically, even real life environments like robotic walking and grasping. And the second column shows the prior knowledge that an agent should have or have access to solve this. And the list of priors that that the agent should possess, it must shrink, and it indeed gets depleted by MuZero. So for AlphaGo, human data, domain knowledge, rules of the game, they are all needed. In just 4 years, DeepMind released the agent where there was no need for any of them. So MuZero is able to play without any human data, without domain knowledge, and without even knowing the rules of the game. So let's see how they actually were able to achieve this. Yeah, so first of all, a couple of words about AlphaGo. So AlphaGo actually had beaten the world champion in Go, Lee Sedol, and there was an interesting actually AlphaGo beaten Lisidol 4-1. So not like 5-0, but lost once. And the feedback from Lisidol was that originally he suspected that that the bot basically will like just utilize the statistical knowledge to make the next move. So we'll just make the moves which are most promising at every step, according to the large database of games that it memorized. But it turns out that actually AlphaGo made some very smart moves and making some moves that even masters they didn't see ever. How was AlphaGo trained? Actually, so why wasn't it like a perfect breakthrough in AI? The reason was that it was trained on a huge database of human data. So actually, they did something like imitation learning in the sense that they pre-trained their neural network on the huge database of recorded games. So people are playing over the internet, and all their games are recorded, stored in the database. They took it, including the database containing the games of the best players in Go, and they, so to say, pre-trained the model on this. And that was fine for AlphaGo, but for the future development of AI, it was just not possible because if you want to solve a new real-world task, you don't have any experience. Normally, you don't have any experience of people with it. So you want to actually solve any task possible without humans even like ever seeing or trying to solve this task. So this actually this attempt to get rid of any human data and domain knowledge, it led DeepMind to AlphaZero. So AlphaZero, it led first to AlphaGo Zero, and which doesn't use any human data, and eventually led to AlphaZero, which doesn't use human data and is able to solve a wide variety of games. So how does AlphaGo Zero and AlphaZero gets trained? It actually plays with itself. So the agent starts with like random initialization of its knowledge and starts playing it itself. So this is not possible for, probably it's hard for like a single person to play with itself, with themselves, because you still need to choose which side you prefer. But for the algorithm, it's possible to make it absolutely unbiased in the sense and be able to make both moves, both by white stones and black stones interchangeably, and still try to win on both sides in its order, right? So this is the way. This was a step further in getting to the true artificial general intelligence, basically getting rid of any human experience with the environment. The step with AlphaZero was actually to make the agent generalize more. So not only some specific problem, but actually absolutely the same agent, the same, so to say, software code for it, it should be able to solve different environments. Of course, the architecture of the agent is the same, but the training should be done like separately on its own domain. So the agent should be trained on Go and chess and shogi separately or together. Doesn't matter that much. It's not that the agent trained on Go is able to play chess and shogi. It's that's not what is expected from the AI at this stage. What is common? What is common for all the methods that DeepMind suggested? They actually rely heavily on Monte Carlo tree search, or MCTS. In fact, people are very good in planning their nearest future, distant future, and if a human can do something, then most likely an algorithm can do it as well. The question is how to formalize it in an algorithm and make a software code of it. In 2008, researchers proposed the algorithm called Monte Carlo tree search, which basically does the same as people do. So people try to select the range of possible actions that they can do, and look ahead in the future, in the model future of the world, which sits in their brains, to actually predict what's going to happen in the future if they do this or that. And then with the most difficult outcomes or the most uncertain, they continue this process. So if I do this, but then I do this list of actions, and after I'm doing another step, I can actually do some extra actions, and this actually is building the tree of possibilities. And you are building the tree of possibilities, and what you need to do is actually to find the out of all these leaves that you have. So the leaf nodes, they are, so to say, the outcomes or the stages until you are able to find the best for you. So this is perfectly formalized into MCTS algorithm, which is a perfect paper. It's just 2 pages long, very compact. It basically has the selection stage where you select the action. It has an expansion stage where you actually select the sequence of actions at your planned future, and then you actually adding nodes, the projected states of the environment to the tree. So you are basically expanding the tree, building it, growing, and in process you actually simulate either the environment to the stage or your idea of the environment. So this will be very important in the when we'll be speaking about MuZero. So in the original paper, they relied on simulation of the environment. So the kind of what's this MCTS about is actually about how to make just one step, how to make a good decision about the next step in reality by simulating or modeling your future moves. So you're actually not making any moves, but you are thinking about multiple outcomes in the future. And the backpropagation stage is basically selecting the best outcome or collecting the statistical information about what what actions bring to which results. So this is the essence of Monte Carlo research. And let's take a look how it is applied to AlphaZero. So again, I remind you that when we are playing the game, we're at any moment of time, we need to make a decision which move we make. And now we are at this stage. So we are not playing the game entirely. We're just thinking about one single move. So we are at the state of the game like this. And we're making some action. Then the model of the environment gives us the next state. So this is the process of how AlphaZero builds Monte Carlo tree. And here it is important that for the modeling of the next state in which they will be in the future, they use the model of the environment. So this is the actually the rules of the game. So the rules of the game say that if you make this action, then you will get to this stage. And there is a list of possible actions. There is a list of forbidden actions. Everything goes into this model of the environment. Speaking about how actually the decisions are made, so how reinforcement learning works in this setup is that in AlphaZero they have only one neural network. It is F. So F here is a neural network, and it's an imaging neural network because we represent the board as a set of pixels. So as an image. For chess, it is 8 by 8. For Go, it is 19 by 19. We represent it as an image, and the neural network. Its purpose is actually for the current state to provide what is the best. Not only what's the best action, but what's the distribution of actions across all possible actions. So the distribution of probabilities of getting the highest outcome across all actions is called policy. And that's what the neural network should actually learn. So the primary thing is policy, and the auxiliary thing is value. So what is value is for Atari games, it is so for Atari games it is score. For Go and chess, it is the probability of winning of the current player. So for Go and chess, the probability of winning is between 0 and 1. And actually, if you've been like watching poker, for example, so the algorithm, which is not neural network, they just exhaustive search, it actually shows the probabilities of winning and losing for each of the poker players. So this can be calculated and this can be learned. And basically at every stage, at every step of Monte Carlo research, we predict policy, we predict value, and then repeating this 50 times, we actually get some statistics. So what will happen in the future, in the nearest future, and we make a more educated decision about our next step. So this Monte Carlo research procedure is repeated at every step of AlphaZero playing, either with itself or with with people. So what's problematic? What's problematic here in this setup of AlphaZero? The very existence of these rules. So just imagine we don't have any. Just imagine we don't have any. We don't know the rules of the game. So what? And for example, if we as human beings live in society, we basically don't know the rules of the game. There are some laws, but actually you have to discover the rules on the go. So to bridge this gap, DeepMind decided to solve Atari games. And Atari games, yeah, let's see what's Atari games, but basically it's a good example when you don't know the rules of the game. Atari game is a console, game console developed and was popular in the early 1980s, so a very old one. And this console has a processor of, if I'm not mistaken, 16 megahertz, and its RAM size is 128 bytes. So it's not like kilobytes or megabytes, or like nowadays you won't be surprised with a computer with a memory size of 128 gigabytes, but this was 128 bytes. It was a very weak computer, but nevertheless very popular in 1980s. And the most important feature of this game was that because there was no any rules, you just see the picture, you have a controller with several keys, you have joystick, a button, and that's basically it. So a very simple interface, but very hard to play for humans and for machines as well. What were the games for Atari? So this is the classical one, Breakout. This is also, I think, quite well-known Pac-Man, or specifically Mrs. Pac-Man game. So it appeared in early 80s. Space Invaders, and this game I don't remember what's its name. Maybe if someone knows, write in the comments. Yeah. So the point is that it's just these are RGB images, and let's see how MuZero solves this situation. So for AlphaZero, we've already seen this scheme, how MuZero works. So what's the ingenuity behind MuZero? It's actually the way they move from the image of the board as the state to some internal high-dimensional representation. So this procedure is called embedding. So you embed like every image in your image space is a dot in high-dimensional space, and you can embed it into a lower dimensional space. And the size of this space is like typically embeddings have sizes like 128 floating point values, so it's a vector, or something like 4K values, so a long vector. And this is basically the way to encode your state. So if you can see what's there on the board, this is obvious for a human, but machines they may prefer some other representation, and the vector of floating point numbers is a very good representation if it contains all the necessary information. So this is called an encoder, and this encoding process this is heavily used in natural language processing, where words are encoded as vectors. So in the same manner, you can encode images as vectors, and what it helps you to actually achieve. So if there is an analogy with humans. So people, when they are planning ahead, they are planning in their own, so to say, fantasy or model of the world. So the world is huge, and the image that a person sees with eyes, it is kind of big. But you don't need the entire image, all the details and textures to actually think about the future, to plan ahead. And you actually compress this information somehow into your internal representation, and no one knows what's the mapping. So the mapping for every person is different, and it's somewhere wired inside brains, how you actually understand the world. But nevertheless, having some sort of compression of the world, the model of the world, you can actually start planning with it without trying to simulate the world, because you with the real world you can't get the precise future if you do something. So you have only one attempt to check what's going to happen. But you can have multiple simulations in your brain, and that's what MuZero actually does. So you get rid of the image representation of a state into, and you go with the embedding representation of the state. So what you can do now for Monte Carlo tree search is actually create a separate neural network, which is called a dynamics network, which is the model of the dynamics of the environment. So the way actually the agent understands the environment. And now this network you can train with backpropagation, and regularly as neural networks are trained to predict the next state in which the environment will go if you start with this stage, with this state, and take this action. So it is a bit hard to predict future images, but if you predict the future embedding, then seems that this goal is way easier achievable by the learning process. Right. So once you extract the dynamics network, you kind of are left with multiple networks, multiple neural networks. So you don't have one policy and value network. You have three networks. So first is the observation network, which embeds the image. Another is the dynamics network, G, and F is the kind of almost old style policy and value network, which is a regular MLP, whereas H and G, they are actually convolutional networks. So they are, in MuZero, they are ResNet based. Right. So what's the conclusion from here is that there are ways to formalize the way humans think and behave. And the next outcome is that not necessarily you have one neural network. Even with GANs, you see that there are multiple subnetworks. Here we have three networks, and they are trained simultaneously. Nevertheless, they are separate, essentially. Right. So let's see how Monte Carlo research works in case of MuZero. So you can see that first we transform the image of the board or an Atari image into the embedding vector of the state, and then continue multiple steps with the dynamics network, actually exploring the tree of possibilities. And as we explore, we compute the policies, so actually the probabilities of taking each of the actions, and we explore the value function. Right. So we in MuZero they repeated 50 times to build the tree. This is some trade-off between thinking too much about every move. If you make multiple traverses across the tree, and the ability to think further ahead. So yeah. With the and again, I already mentioned that these three networks, H, F, and G, representation, prediction, and dynamics, they are different, and with probably you may be interested in seeing what's the real values of these representations are. So Atari image. So here we have the image of a Go board, but for Atari, the resolution of the image is 96 by 96, and the number of channels is not 3. So earlier said that the agent sees an RGB image, and there are 3 channels, RGB channels in the image, but actually it's 3 times 32, and 32 is the number of historical frames that the buffer keeps. So it's very important to keep the historical frames and to stack them together in one tensor. The reason for this is that with a single frame, you don't know the dynamics of movement of maybe Super Mario or a ball in Breakout, for example. So by stacking the historical frames over the color dimension, you can actually keep the history of motion, of the recent motion over several frames of the image. So basically having a video snippet. So MuZero doesn't look at the single image, it looks at short video snippets of the game. And an interesting thing about the state, so normally a state is represented as a one-dimensional vector, but for MuZero, they left the spatial dimensions intact. So the representation network, it is a ResNet network with several blocks and several strided convolutions, which reduce the resolution from 96 to 6 each dimension, height and width, but not to absolute minimum, to 1 where they can be squeezed, but to some values. And actually the shape of the state, it actually it is preserved over the dynamics, because for dynamics network, the input shape and the output shape must be exactly the same to allow this recursive process of exploration. Right. And so far we've been talking just about deciding what to do on a single step. But the Atari game, it lasts for multiple frames, like tens, thousands, maybe tens of thousands or 100,000 frames. So we've been playing it for a while, some minutes or if not hours. And this Monte Carlo research, it repeats at every step. So we expand the tree of our planning, we decide what action we take, and then we hand over the control to the environment, and the environment makes a step. And then again, we repeat the process by running Monte Carlo research. So this is performed until the environment says that game over, we are finished, and there is a special flag that environment returns that says to the modeling that the game is over, and we need to restart with a new episode. And again, if you had noticed so far, we only talked about inference. So there was no any training at all in this process. And this is typical for reinforcement learning. With reinforcement learning, you don't have data. So when speaking about like regular machine learning, you normally think about the data set on which you're gonna train your model. But with reinforcement learning, there is no any data set. There is only an environment, and you need to actually generate data set by yourself on the go. So that's what happens with reinforcement learning. We have two separate conceptual processes. One is self-play, and another is training. So self-play is basically we take the current state of our model, we take our current agent and make it play with the environment. This creates the experiences or episodes, and these episodes are stockpiled in a replay buffer. The replay buffer is not like a pure buffer like memory buffer, but it's actually a queue. It's a queue where you put your new experience on top, and on the bottom, when the replay buffer reaches some limit, like 10 or 100,000 of episodes, the old memories, they get thrown away. While this replay buffer is preserved, another process, a training process, is actually sampling batches from the replay buffer. The replay buffer is 100,000 samples. Training may sample 1,000 samples randomly and perform the optimization step. So update the weights of the model so that it, in the hope that it will play better in the future. And once the weights are updated, the weights are spread back to the self-play processes. So this like technical implementation for reinforcement learning setup. This replay buffer can be very big, so it can be tens or hundreds of gigabytes and actually take all the RAM of your server. Right, and when speaking about training, so the second process which is running in parallel, this is relatively standard, but for MuZero, it's very important to have this so-called temporal difference learning. How does it work? So we, in our experience that we've been playing before, we memorized what were the states of the game and what actions we took, and now we can. So we have this series of actions, and we build the network of, we build a chain of neural networks, so the representation network, and we build a chain of dynamics networks, and here the agent doesn't play. All its actions actually are memorized and recorded. And why do we do this unrolling? Why can't we learn from every single frame? Because we have a dynamics network. So to train a dynamics network, we need this transition. So the losses, they come from here. So we have like 3 tabs where losses start: here, here, and here. So we have policy loss, we have value loss, but we basically kind of don't have any ground truth for dynamics network. But it will be learned through the F subnetwork. So you can see the gradient comes backward in the backward direction of the arrows. The gradient will come here and will follow the G network. So the dynamics network, it doesn't, it learns like a little bit a little bit implicitly. So the gradients, they go through the dynamic networks and follow here to the state of the board. So this is a very handy trick. In fact, you can train some subnetworks without ground truth. So this is a very smart setup and probably very good to keep in mind for probably future designing of your own networks. Here I wanted to show that the loss function is kind of bulky and complicated, but actually it's this is fine for solving real-world problems. So it's not that you have one loss function and that's it. So for MuZero, you have 4 components: the reward loss, the value loss, and the policy loss. And the policy loss is kind of the essential here. Reward and value are auxiliary losses, which help with convergence. And also here you have L2 regularization for the weights. This is the standard thing. So it's not that scary as it seems. But anyway, also the takeaway from here is that typically you need multiple losses to solve a complex problem. And another thing that I wanted to mention is DeepMind in MuZero, they suggested the reanalyze technique. So basically, this is also inspired by how people live and think and get by, in the sense that if you have very few experiences, so for example, if you, I don't know, or you don't have, you don't want to have many experiences. For example, you broke your leg some like 10 years ago, and to learn as much as possible from it over years, you are getting back to that episode of why I broke my leg. So I should have done this and shouldn't have done this risky thing, even though there in the past I thought that this is not risky. Now, like 10 years from then, I reanalyze, rethink my past experience, and find it risky, and I would do it differently back then. This is actually the approach, which is also formalized and put into code by DeepMind, actually to take the trajectories from the replay buffer and update it with the MCTS predictions for every step based on the current most up-to-date state of the agent, and then put it back to replay buffer. So you don't throw away your past experience frequently, but you update them time to time to actually improve your overall learning and convergence, getting to the best to your best self. Right. And about the application. So, okay, like playing Go or playing even Atari, it's still just fun. So nothing real world here. But there are actually ways to apply it in practice. One of them is just wanted to introduce Smarts. This is the simulator, the multi-agent simulator for autonomous driving, developed by my colleagues in Canada back then at Huawei. So this is the gym environment which is able to be connected to any reinforcement learning agent. So this is basically the virtual playground for multi-agent autonomous driving. So this is definitely helpful. So we can finally apply reinforcement learning to solve, to make autonomous driving like possible, to see the self-driving cars on the roads. And still, autonomous driving is somewhat fancy applications. The more practical one, even more practical, very pragmatic, and probably unusual is messing with compilers. So, but how can we play the compiler? So typically, compiler just compiles and that's it. But it turns out that you can pose compilation of code as a game and connect it to the reinforcement learning agent that will play it. So engineers researchers from Facebook Meta, they released compiler Gym, and it's a Python environment where you can instantiate an LLVM compiler, and what the environment basically does is allows you to control the compiler keys that you say. So there are like optimization keys, O2, O3, O0, loop and roll keys, and so forth. So there are tons of keys, and you can actually benchmark some Q-sort, for example, algorithm by trying different keys, compiler keys, and actually your reinforcement learning agent can play with the keys and their sequence, not only enabling or disabling them, but also putting them in proper position, because the sequence matters in this case, right? And basically, the interface is very simple. So you get the state, you sample some action, basically isolate this key to put next into the command line, and you make a step which makes the compiler Gym memorize the keys, and then it produces the feedback in the form of runtime or instruction count, whatever you optimize. So finally, we starting to have real-world applications for reinforcement learning agents, and this is very nice to see. So yeah, that's it. That's what I wanted to present to you. So this was so MuZero basically is a confluence of technology, science, and philosophy. And this, I think, it's very good to know how it works. I'm giving word back to Alina. Right. It seems that we. Okay, you're back. Any word to you?
So am I right that you are ready and you welcome everyone who is interested in this topic to write you directly in Telegram or other resources?
Sure. So with this QR code, you can find my Telegram, WhatsApp.
Let me check if it works.
LinkedIn.
So everyone who is ready and who wants, you may ask a question by voice right now or write directly to Dmitrii. Okay, I see the message. Oh, there is a question in the chat.
I think that's the question from Andrei.
Andrei Savchenko. Okay, yes.
So speaking about car simulator, how to add real scenes to learn the models to recognize scene. So yeah, this simulator, it works on the level of metadata. So it works on the level of extracted 3D bounding boxes. And I think it's a common practice these days. Majority of the companies work like this, so they heavily split the pipeline, the autonomous driving pipeline, into the perception, which produces metadata as 3D bounding boxes of cars, pedestrians, bicyclists, so forth. And then the further logic, it can operate on bounding boxes, and this is what can be easily feed into simulator of scenarios and so forth. So smarts, it specifically intends to train planning subnetwork of the autonomous driving pipeline. Of course, it won't help in almost in any way with perception. So perception, modeling both perception and prediction and planning altogether is very complicated. I think it still gets split into two parts, perception and everything else.
So I think that we have to stick to time limits. Thank you for your presentation. Thank you for your speech. I hope that everyone who visited this meeting will find this very useful, and I will also upload the recording for open access for everyone who is interested in this topic. And thank you for joining us today, Dmitrii.
Thanks for inviting me. It's a pleasure.
Yes. So let's stop the meeting. Thank you. Goodbye.
Bye, everyone.